Chase, stop playing Pokemon. All right, areas between curves. So that's exactly what we're going to try and do. Instead of interpreting the integral of a function as the area under a single curve, I want to figure out how I can find the area between two curves, so that region S along some interval. And the idea is pretty straightforward. So I'm going to start off with my own graph. I'll have you sketch this along with me. So sketch yourself a graph. Let's call this one arbitrary graph F. And then below that, I'm going to sketch arbitrary graph G. And then I want to know what's going on for those on the interval from A to B. And I specifically would like to only know the region between them, right? So I want to figure out how to set up an integral that will do that. And so it's actually, I think, pretty intuitive, which is if I took the integral from A to B of f of x dx, do we all agree that geometrically I can think of that as all of this area, the area below the graph of f to the x-axis between A and B, yeah? That's everything below f down to the x-axis, right? If I took the integral from A to B of g of x dx, that would be this area, the area below g down to the x-axis, yes? If I just want to be left with the area between f and g, subtract them. And that would leave me with this, yeah? Well, integrals are really just infinite sums, right? So they follow basic rules of addition and subtraction. And we also have this property that if we're integrating from a to b f of x dx and we're subtracting the integral from a to b of g of x dx, we can actually just write that as a single integral. That's just the integral from a to b of f of x minus g of x dx. So pretty intuitive, yeah? If you want to find the area between two curves on an interval, you're going to integrate the difference between the curves. Which direction? Top minus bottom, right?
Wait.
Yeah.
Yeah.
The one on, even if it's below the x-axis, and we'll discuss that. Whichever one's on top minus whichever one's on bottom.
Okay.
Now let's talk about some special cases. We know that when we just integrate a function that's below the x-axis, we end up with negative area, right? So let's draw, actually let me do this. Let's draw a new situation. So what if it was like, that was bad. Still bad, but acceptable. All right. So let's say f is above the x-axis and g happens to be below the x-axis. Does that mess us up between a and b? Does that change my rule at all? This is considered negative area, right? But when you subtract negative area, you end up adding positive area, don't you? So just think of it like a number line. If I want to know the distance between two numbers on a vertical number line, and let's say this is positive 5 and this is negative 2, you take the same approach regardless of what the numbers are. You do top number minus bottom number, and that gives you total distance. Because what's 5 minus negative 2? 7, right? So no, it does not mess us up at all if one curve is under the x-axis or if both curves are under the x-axis. If you want the area between two curves and you integrate top minus bottom, you will be left with the positive area between those two curves. Does that make sense? Always. So, one thing to understand, if you're just integrating a single function, you could end up with a positive number or a negative number, depending on if that single function is above or below the x-axis, right? If you're finding the area between two curves, your area should always be positive no matter what. Because now it's no longer net area, it's total area between two curves. Does that make sense? All right. And it's pretty much that straightforward, folks. We're just going to apply that logic. Now, we are going to talk about what happens eventually when we have two curves that cross each other in the interval that we're talking about. So if you had f is like this, you had g is like that, and this is A, and this is B, and you want this total area, there's going to be an additional step, but that step is pretty intuitive as well, and we'll jump that bridge when we come to it, all right? Let's get to a couple of examples here. That's everything we just went over, just kind of broken down into really, really fine detail. All right, find the area of the region bounded by x squared plus 1, above and below by y equals x, and then bounded on the sides by 0 and 1. So the only real tough thing about this is making sure you can, because in this case, they've given you the graph, they've told you which is on top and which is below, but that's not always going to be the case. Sometimes I'll just give you two functions and say find the region bounded by those functions. Then you're going to have to make that determination yourself. That's not too crazy, though, and we'll do an example of that. All right, but in this case, let's set up our integral. Area equals the integral. Which function's on top? So I'm going to do x squared plus 1. Which function's on bottom? So I'm just going to do minus x. Something to be careful of, if the function on bottom has multiple terms, when you subtract it, you need to put it in parentheses, right? So you remember to distribute that negative to each term. Dx. And now we're looking left to right. What's the left endpoint of my region? What's my left boundary? 0. What's my right boundary? If you're integrating with respect to x, your limits of integration should be x values, right? And I say that now because we are going to do a couple where we integrate with respect to y. Whatever your variable that you're integrating with respect to, your limits are in terms of that variable, right? So 0 and 1. All right, then we just have a basic definite integral that you guys are completely capable of dealing with. So what's the antiderivative of x squared? So we got 1/3 x cubed plus minus half x squared, and we need to evaluate that from 0 to 1. Plug in 1, I'm going to get 1/3 plus 1 minus 1/2. Plug in 0, I get all zeros, right? So 1/3 plus 1, 4/3. It's 4/3 minus 1/2. 8 over 6 minus 3 over 6. There we go. Good. Just a quick check for sanity. Since it's the area between two curves, it should always come out positive, and this does. There we go, and that represents that shaded blue region. So far, so good. Questions? try another one. All right, well, what if you're looking for the area enclosed by two curves, but they tend to cross each other within your interval? You're just going to have to set up multiple integrals here, right? So let's call this C1, and we'll call this C2, and that's the point of intersection, right? So if I wanted to find the total area between those two curves, I'm going to end up setting up three integrals. What's my first integral going to be? Good. Integral A to C1. And what's the integrand? What am I integrating in that region? Yeah, so f is red, so it would be f minus g dx, right? Since f is on top there. Chase, what's my second integral? Plus. I agree. And what would my integrand look like in that case? You got it. Now g's on top, right? John, what's my last integral? What's the last one? So I want to find this region. So my limits are on the x-axis. From what to what? Somebody help? Yes, C2 to B. And what's my integrand? So f is on top again, minus g dx, right? And that's it. Now, a lot of times you're not going to be given these values at the points of intersection. How do you find the points where the graphs intersect each other algebraically? Yeah, that's where f equals g, right? You set them equal to each other and solve for x, yeah? So that's kind of the abstract of how to tackle something like that, and now we'll put it into practice. All right. Let's do it with this one. So I'm looking at the curves y equals sine x and y equals cosine x between 0 and pi over 2. Now you're given a diagram, which I kind of wish wasn't there, but we'll talk about how to do that. So between 0 and pi over 2, sine x and cosine x do cross each other. So to know where they cross each other, I want to set sine x equal to cosine x. Well, this isn't really easy to solve analytically, but you can do it by inspection, meaning sort of guess and check. If we think about when are sine and cosine equal? So think about the unit circle here. Cosine is the x coordinate and sine is the y, right? This is the point 1, 0. This is the point 0, 1. So those are the extreme cases when sine and cosine have one's 1 and the other is 0, right? Somewhere in between there, they'll be the exact same. Well, it happens to be exactly halfway in between, right? Sine and cosine are the same because that becomes an equilateral triangle. What is that angle? What is this, Steiner's class? That's 0, that's pi over 2, so it's pi over 4. All right, so x equals pi over 4. All right, now that we know that's the point of intersection, we're ready to set up our integrals. and I'm going to go area equals integral 0 to pi over 4. Which one's on top for that first region? Stop looking at the diagram. You need to remember cosine starts at its amplitude, sine starts at 0, right? So that's how you would remember that. Cosine starts at 1 at the origin, sine is at 0, so cosine starts out at top. So cosine x minus sine x. And then we'll go plus the integral from pi over 4 to pi over 2, and we'll swap them, sine x minus cosine x. All right, we are going to be dealing with a 45, 45, 90 triangle to evaluate this. So let's see. Actually, I'm going to call it a pi over 4, pi over 4. You guys remember the sides of that triangle, 45, 45, 90? Right, and you can just do 1, 1, rad 2 if you wish. All right, so now that we have that to reference, let's go ahead and deal with this antiderivative. Antiderivative of cosine is, so for this first one, I'm going to have sine x. Antiderivative of sine is, so it's already negative, so it's going to end up being plus cosine, right? And that's 0 to pi over 4. All right, and then the next one, plus antiderivative of sine, you just told me is negative cosine. And antiderivative of cosine is sine, so I'm going to get negative cosine minus sine from pi over 4 to pi over 2. Okay. Well, let's start plugging these in. For the first one, I'll plug in pi over 4. I got sine pi over 4 plus cosine pi over 4. And then plug in the lower limit, and I'll have minus the quantity sine 0 plus cosine 0. You do have perfect symmetry here. So recognizing that, one of the things we could have done, if we recognize that, is just found this area and then multiplied it by 2. But we're doing it the long way. All right. So then plus, plugging in, for the second one, the first one we plug in is pi over 2. So I get negative cosine pi over 2 minus sine pi over 2. And then we're going to have minus the quantity negative cosine pi over 4 minus sine, oh, I'm out of room, pi over 4. Sorry. All right, so let's start evaluating these. Sine of pi over 4, I need some basic geometry trig knowledge. There's pi over 4. In the triangle, what is the ratio for sine? Yeah, opposite over hypotenuse, right? So 1 over rad 2, or if you want to rationalize it, rad 2 over 2. Those are the same. So this comes out to rad 2 over 2. Well, what's cosine of pi over 4? Same thing, rad 2 over 2. And then I have minus sine of 0. Let's go to the unit circle. Sine is the y coordinate. Sine of 0 is 0, right? All right, so I got minus 0 plus, what's cosine of 0? 1. And then I have plus cosine of pi over 2. Now we're up here in the unit circle. What's cosine of pi over 2? 0, minus, what's sine of pi over 2? 1. And then I have to do minus negative cosine of pi over 4, so that's going to be negative root 2 over 2 minus root 2 over 2, right? Just got to be real careful with parentheses on this problem. All right, well, simplifying, root 2 over 2 plus root 2 over 2 is just root 2. And then there I have minus 1 plus, all right. Let's check these parentheses. I'm going to have to distribute that negative, right? Which is going to make both root 2's positive again. So I'm going to end up with plus negative 1 plus root 2. All right, finally simplifying this, how many root 2's do I have? I have 2 root 2, and I have 2 negative 1, so minus 2. All right, so a little trig practice there. I think we're going to have like 1, maybe 2 more examples. We're almost done. All right, well, sometimes, rarely, but sometimes, you're going to see functions defined where x is a function of y, right? So like, you must have done this in pre-calc, but like if you have x equals y squared, what does that graph look like? It's a sideways opening parabola. It's just something like this, right? In that case, let's say I was looking at the function x equals y squared and then also the function x equals y. They do create a region, right? But it's going to be easier to integrate with respect to y. And that's totally fine. You can integrate with respect to y. We're just going to kind of adjust our point of view. Instead of doing top function minus bottom function, and I'll put this back in the context of a number line. If I want to find the distance between 6 and say this is negative 3, how do I find that distance? I do. The distance is 3. Yeah, you still subtract which direction now, because this is a total of 9 between them, right? So which direction do I subtract to get that 9? It's right to left. So when they were functions of x, we did top minus bottom, right? And that always gave us a positive area in between. When they're functions of y and on their side, same idea, except we're going to do rightmost function minus leftmost function. And now since we're integrating with respect to y, our limits should be what type of values? When we were integrating with respect to x, let's go back. There were x values, right? 0 to 4, pi over 4, and pi over 4 to pi over 2. Right, so if we're integrating with respect to y, our limits of integration should be y values. And you're just going to go integrate from the lower y value to the upper y value. Does that make sense? So same idea, we're just kind of adjusting our head like this, like turning our head 90 degrees. All right, so here's an example. Oh, that's not a right minus left. Let's do this one. We're going to jump to this one. So, what is the area of the region in the first quadrant bounded on the left by the graph of x equals y squared over 2, and on the right by the graph of x equals 3y minus 4 for y between 2 and 4? Now, you may not know what these graphs look like, which is fine in this case because they tell you the orientation of the entire thing, right? So the area, we're going to set this up, is the integral. Now, which one is on the right? Yeah. That's a good question. Based on the context of what they're saying, they don't intersect because they tell us which one's on the right and which one's on the left. And if that wasn't consistent, they would say, right? But one way you know these don't intersect is that this is a parabola. It's positive y squared, so it's just a parabola on its side, and it's compressed by a factor of 2. And that's just a linear function. So the most they're ever going to intersect is twice. It's never going to cross in the region, right? All right, but knowing by the context of what they're saying, which one's on the right? The second one. So I'm going to go 3y minus 4. And that means the other one's on the left, so I'm going to subtract y squared over 2. I'm integrating with respect to y. And then they also give us our limits of integration, right? It's from 2 to 4. And that's it. We just have to evaluate that integral. Our variable is just y, right? Let's do that real quick. Antiderivative of 3y. 3/2 y squared minus 4y minus what's the exponent? What's the exponent? Y to the what? All right. And there's already a 2 down there, but we're going to bring an additional factor of 3, so it's over 6, right? 2 to 4. All right, just a reminder, because I can't tell you enough, that when it's something that this complex, don't do that by hand. Let's use our calculator. Let's put the antiderivative in y1. My antiderivative is 3/2. Just replacing y with x squared minus 4x minus x cubed over 6 once it's there, you can just go alpha trace y1 of the upper limit, which is 4, minus alpha trace y1 of the lower limit, which is 2. So plugged in the upper limit to the antiderivative, plugged in the lower limit to my antiderivative. Now I'm just subtracting. That's the shortcut to your y variables. If you have an older calculator, like an 83, that shortcut doesn't work. Here's how you find it one more time. Alpha traces your y variables. If you go to vars, and then you can see the y vars is the second tab in, y vars, and then function. That's where you can find them as well. But we get 2/3. Any questions? Is the bigger the number, the more satisfying it is? It's like when students get mad that an answer is 0, as if you could have just guessed that somehow. Come on.